So let me begin with the following motivating questions. Uh, so the, let's consider these following questions. Number one, can we classify all varieties to birational equivalence? Then, can we find a non-singular curve in each birational class? And third is, can we classify all non-singular curves in each birational class? Or maybe in general we can talk about varieties, not necessarily curves. So can we classify all non-singular curves or non-singular varieties uh, in a given birational class? So in general, all these questions are too hard to answer as of now. But today I will talk about a special case of question 2 and 3 where we'll I will only consider for curves instead of in general varieties, and I will in fact show that there is indeed exactly one non-singular curve in a given birational equivalence class. So here question number 2 asks about existence of a non-singular variety in a class, and uh, question number three is talking about classifying them. So I will so the answer for this is today uh, we will see in each variational class there exists a unique non-singular curve. Okay. And we'll in fact show the equivalence of the following category. So first is finitely generated field extension of transcendence degree 1, field extensions of a fixed base field K of transcendence degree 1 where K is algebraically closed, and non-singular projective curves with the maps being here the maps being K algebra homomorphism in this category, and here the maps are in the dominant morphisms. So with each say capital K, which is of transcendence degree 1 and finitely generated over small k, I will associate an object, something which I will denote throughout by Ck. I will define what is Ck. Okay. Now before doing everything, let me fix some notations and all. This notation will be followed throughout this talk. So let me define first this special terminology. So I'm not defining what's a DVR and all, but I will define say a ring R is said to be, of course, commutative with identity is said to be a DVR of K over small capital K over small k if first of all it's the usual definition of a DVR, and secondly the valuation should vanish on small k star. Okay. And second terminology is we say K is a function field of little k if function field of little k of dimension 1 if capital K is finitely generated uh, field over K of transcendence degree 1. So exactly you can imagine capital K to be a function field of a curve over small k. Then this exact condition will hold. Okay, now so so from now on I will assume K to be algebraically closed. So throughout from now on K will be algebraically closed. And so basically we want to show the equivalence of these two things. So given such a function field of dimension 1, I need to associate a projective curve that has to be non-singular. So what we will do, so as I was saying, so this K you can think of it as a function field of a non-singular curve, you can say. Okay, so if you have a non-singular curve Y, so if Y is a non-singular curve, then you can look at all its local rings, right? So the local rings OPY. So these are what? These are of course Noetherian local domain of dimension 1. And moreover, because we are talking about non-singular curves, these are regular rings, which is same as saying it's a DVR. So this is a DVR of K with little k, right? Because the valuation exactly vanishes on small k. So what we get is actually we get a map. So it takes if you have a non-singular curve y, you take it you take a point and you take the local ring. And the first result, so we can call it a lemma. That so this assignment is 1 1, or more generally, as the lemma we can say if you have 2 points, say PQ, such that the local rings are contained in one another. Say suppose you have a quasi-projective variety. So let Y be a quasi-projective variety. And you have 2 points such that the local ring at one point is inside the local ring of the other point, then P is equal to Q. The proof is pretty simple. What you do first, one can assume that both P and Q doesn't lie on a common hyperplane. That you can do by some linear change of coordinates. And let's say the hyperplane is h0. You can further change the coordinates to make it h0. Okay, so in that case, I will get both P and Q is in Y intersection Pn because it's a projective minus H. So, but this is an uh, affine variety. Right? So for affine, if you assume, you can now without loss of generality assume Y is affine. But in that case, the local ring are exactly correspond correspond to the maximal ideal. So this will correspond to if say A is the coordinate ring, affine coordinate ring of Y, then this is exactly this, and this is like this, but both of them are maximal, so they are exactly the same, meaning the local rings are or the points are same. Okay. So in particular, the assignment above P going to OPY is a 1 1. This is 1 1. Okay. So now, Okay, so let me, so this is one of them. We'll use this result a number of times. So let me call it lemma 1. And there's another lemma which, if time permits, I will try to indicate a proof of later. So again, k is a function field of dimension 1 over small k. And you take a point this. And you take, okay, so I have to fix a notation. Okay, so let me define what is ck. The ck that I wrote here. So I will define ck as collection of all dvr of k over k. So it's just a set as of now. We don't know whether it is a variety. In fact, we have to put a topology on it to make it a topological space at first. So, and the topology that I will take is just the cofinite topology, meaning the open sets are exactly complement of finite set, but cofinite topology. Okay, and the motivation behind taking this topology comes from this lemma, which reads as follows: finite. So, what does this mean? By the way, as a matter of another notation, because we will take CK as topological space, or more generally, we'll show it's a quasi-projective non-singular curve, which is a main theorem of this talk. I will often refer to the elements of CK as points. So sometimes I will write it as P, which denotes a point, or sometimes, so P is a point means it's a DVR of K over K. Sometimes I will also write it as R of P. So don't get confused that this R of P notation is just to emphasize the fact that P is actually a DVR. So R of P is not a localization of R at some prime idea. So just to make sure that there is no ambiguity regarding this. Okay. So if time permits, I will indicate a proof. Let me not get into that. But as an important corollary, we'll get the following. So this corollary is of lemma 2. Let me call it corollary 3. I'm just naming them in the order that I'm writing. I'm not naming the lemmas and corollaries in different order. So this will say that any dvr of k over k. So let R be a dvr of k over k, which is in ck, is isomorphic to local ring of a point, isomorphic to local ring of a point for some affine variety. Now, this corollary will basically follow from how this lemma is proved. Basically, in this lemma will construct such a affine variety or such a finitely generated small k algebra. Okay, that is same as saying an affine variety. Okay, so if time permits, we'll see the lemma and of course we'll see the corollary. It's an easy corollary. But we'll use the corollary to state or to in the proof of the main result. Anyway, so okay, so now the title of the talk was about abstract non-singular curve. So far we haven't defined what's an abstract non-singular curve. So for that, uh, so we have CK and we can talk about. So firstly notice it's an infinite set because for distinct points P, the local rings OP are distinct, right? That follows from lemma 1. And there are infinitely many points P in say Y. Okay. So then they're all distinct and they all belong to CK. So it's an infinite set. So this cofinite topology is not the discrete topology, just to be sure. Okay. And because we want to make CK into a variety, it's important to know how the regular functions on CK looks like. So we'll define a regular function on an open set. So if U is an open set, meaning it's CK minus some finitely many points, we will define the ring of regular functions as RP. So these are points in U, and you just take the intersection. And you notice this fact that so you take an element in this local in this ring of regular functions on U. This defines a map from this to this. How? You take a point P. Now F belongs to P, right? So so for example RP, again the same notation. So RP is a DVR, so it has a unique maximal idea. Let's call it MP. So you can look at F bar inside RP modulo MP, which is basically the residue field, which is K. So indeed this defines the map from U to K. Okay. And now okay, so how does this follow? That's I think pretty easy because of the last corollary. Because this R is a local ring of OPY, so the residue field has to be exactly the base field. And now if two of them say, so firstly notice this is inside K, right? Because each R, K is basically the field of fractions of each R. And also notice that if you have 2 points f and g which defines the same function, that means so for two elements f and g in the OU, suppose they define the same function from U to K. That means what? That means their difference is zero in the residue field for infinitely many points. For infinitely many. Right? Because this set Ck is infinite and U is basically complement of a finite set. So it's in particular infinite. Now by the lemma 2, this will exactly mean that f is equal to g. Okay, and how does this follow? This follows because of the easy fact that an element x is not in R is same thing as the element 1 by x is in MP. So here the element f minus g is in MP, meaning you look at 1 by f minus g, that's uh, not in R. Okay, that set is infinite, meaning that f minus g has to be 0, otherwise this is not possible. So this follows from lemma 2. Okay, so indeed what we get, so for each element, okay, so you get kind of a 1-1 thing, and so we get elements of OU can be identified as functions from U to K. And now if you have any function of K, uh, that can be also seen as a regular function on some open set, right? And so what I'm trying to say is, if you have some element f in K, so that again follows from lemma 2. So if you have some K, now it cannot belong to R for finitely many R. Meaning what? For all those finitely many things, except you just remove those finitely many things from CK. That's an open set because it's cofinite topology. So that's an open set, and let's call it U. So uh, that's in RP for all P in U. So that's a regular function in U. So indeed, so we get the function field, which is defined as the ordered pair of an open set and a regular function on it, can be identified with K, right? Can be identified with K. So the function field of CK is exactly K. That's the important thing to notice. Okay. So, and in fact, we'll exactly use this. So what we get? We started with a dimension 1 function field, capital K. We attached a topological space CK, and we then look at its function field. And by the way, so far it's not a variety, but the function field in the sense you can think, because we are specifying the regular function, so we can talk about function field. And that function field, you get that K back again. Okay. So basically, in this equivalence of category, you go from K to CK, and the other way you go from Y to function field of Y. So one part is identity. That's obvious from this nice observation. Okay. Now let's come to the definition of an abstract non-singular curve. So an open subset of CK is said to be an abstract non-singular curve. Okay, so with the induced topology, okay, that means it's a subspace topology, not right. And we'll see that any such abstract non-singular curve is isomorphic to a quasi-projective non-singular curve, and vice versa too. That means if I give you a non-singular quasi-projective curve, say y, you can show it is uh, it's isomorphic to an abstract non-singular curve. And if I give you an abstract non-singular curve, you can show it as quasi-projective. So in particular, if I give you the curve itself CK, that's an open subset of itself. So that should also be a quasi-projective curve. That will be a main theorem. But before going into that, let me do the easier one. This is in our order. This is theorem 4. So any non-singular quasi-projective curve is isomorphic to an abstract non-singular curve. And the idea of the proof is simple. In fact, the proof itself is simple. So you start with a non-singular quasi-projective curve y. So let y be a non-singular quasi-projective curve, and let's call its function field to be k. Suppose k of y is k, the function field. So then obviously we have a map from y to ck, which is just p going to o of p. Okay. And we have already seen this is 1 1, and I will define u to be its image. So it's by onto on its image. And moreover, so there are only two things to check, that phi or maybe u is an open subset of ck, otherwise it won't be an abstract non-singular curve. So u inside ck is open, and number two is phi is an isomorphism. We know phi is a homeomorphism. So number two is so you have to check the regular functions. The pullback of regular functions are exactly regular functions in the open sets of the domain. Okay, so number two is phi is an isomorphism onto u. And so let's see point number two first. So and that's obvious because the on u the regular functions are just the elements of this, and under the map phi, this points p goes to the regular functions of this. Okay, oh sorry, this should be u, and this is y. So this is exactly the regular function on any open set v, right? So if v is an open set of y, the pullback of regular functions are exactly this. Okay, so this should be like v. Okay. Now, so this follows that phi is an isomorphism, and the last thing we have to show this U is open. Now, because we are talking about cofinite topology, it's enough to show that U contains something non-empty open, right? Because then there is something inside U which has a finite complement. So U itself will then have to have a finite complement, right? So now because any variety has a base of affine open set, you can assume that Y is affine, which say affine coordinate ring A. You can assume Y is affine with coordinate ring A. Then we just have to show that U is open. So what you do is, so A is a finitely generated K algebra, and K is a fraction field of A. Right? That follows from basic properties of affine variety. Now suppose A is generated by, suppose A is generated by x1 to xn as K algebra. Then A is in R of P if and only all these xi's are in R of P. If and only U is intersection of Ui, where Ui is all the points in Ck with xi is in R of P. Okay. Now each Ui has a finite complement by lemma 2. So each Ui is open and it's a finite intersection of open things. U is open. Okay. So by lemma 2, this follows. Okay. So we get that any non-singular quasi-projective curve is an abstract non-singular. And the last and main theorem is to show the converse of that thing is true. In particular, the Ck itself is a quasi-projective non-singular curve. Okay. So, but to show that, so okay. So we need another extension property, which I will probably just state for now because the proof actually is not needed. Okay. So let me just state this. So let me just state this thing for now. I don't need the proof. So I can write it as a proposition. So if X is an abstract non-singular curve, and Y is any projective curve or more general variety, then any map from X minus P to Y, map means morphism, can be extended uniquely to a morphism from X to Y. So this basically gives that in our case, uh, because we are talking about mm, abstract non-singular curve is cofinite topology, CK with cofinite topology. This just said that if you define something on an open set, you can extend it to the whole set. That's it. Because the complement is then finite, so you can apply this proposition finitely many times to get that. And the main result finally will show that CK itself is an abstract non-singular, or CK itself is a quasi-projective non-singular curve. I will do it next time. And the idea of the proof is pretty simple. You just cover CK with finitely many affine open neighborhood, and then you take the projectivization. So each affine open neighborhood you call it ui, u1 to some ua. The finiteness follows because you're talking about cofinite topology, so it's quasi compact. So each affine neighborhood you call it ui, that is isomorphic to some vi, which is affine, which is in some a, say ki. So you can think AKI inside PKI, and then you take the projective closure. For each I, you thus get a map from U or UI to some say projective closure is YI. Now, by this proposition, those maps phi I can be extended uniquely to something phi I bar, which is from the CK to YI. And then you take the product map, the diagonal, and then you take this projective closure, and then you eventually show that it's a isomorphism, meaning it's a homeomorphism, and the induced map on the local rings is an isomorphism. So that's the idea of the proof. I will try to indicate it next time, and also if time permits, uh, I will show the brief sketch of the proof of lemma 2, because the proof of lemma 2 is quite interesting, and it's basically some application of algebra and some properties of Dedekind domains and DVA. Okay, so I will stop for now.